Welcome to the Aspen Center for Physics Public Lecture Series. The Aspen Center for Physics was founded in 1961 by local physicist George Stranahan with Michael Cohen and Bob Craig. The center provides a serene environment in which almost 1,000 prestigious physicists from around the world, young postdocs just out of graduate school to Nobel laureates, come together during winter and summer sessions to share, discuss, and initiate new research.
It took only 2 days at the center before I realized that this was what I had always dreamed doing science would be like. The beauty and peacefulness of the center is a really important asset to us. It is our opportunity to be cut off just enough from the daily grind to have lively discussions at the blackboards, share meals out on the lawn, gaze at the surrounding hills, and actually think about physics.
Thinking initiated at the Aspen Center for Physics, from biophysics to neutrinos to the outer reaches of the universe, has provided the underlying logic for the MRI, the CAT scan, and laptop computers, and will in the future provide the logic for innovations that will transform human endeavors.
Good evening again, and welcome to this Heinz R. Pagels public lecture. My name is Adi Stern from the Weizmann Institute in Israel, and I'm pleased to welcome you, and it's my pleasure and honor to introduce my friend Professor Shankar from Yale as today's speaker. So before I say a few words about Shankar, 20 or 30 minutes only, let me just say you are all very much encouraged to sign up for the email list of the Center of Physics. It's out there on the table, and you'll get lots of information about public lectures, dialogues, and kids lectures, and whatever else the center is doing. Now, you all, I believe, read this autobiography, or maybe biography, of Shankar. Exams will be given at the end. So I will not repeat it. It details the road he has gone along from India, from engineering in India to Berkeley, PhD in physics at Berkeley, then to Harvard and Yale, where he is now for many years. He has carried out lots of works on high energy and condensed matter physics, two branches of physics whose details I will not get into. What I'd like to say only in the half a minute left is a few words about what he has and what he doesn't have, based on sort of a long, not very long familiarity with Shankar. So his works are, from what I saw in these years, all show the same four characteristics. One is he's deep. The second one, he has a very clear way of thinking. It's a clarity of thinking that goes along in the books he wrote and in conversations we had and in the papers that I read. The third is he has a passion for physics. Passion. Most of us physicists are passionate about our field. He stands out among most of us. And for those of you who know him and wonder when am I going to get to the main one, then number 4 is, of course, the sense of humor. Well known within the circles of physics. That, of course, comes at a price. You cannot have all these good characteristics without losing something, and the price he pays is that he doesn't have the mega ego that many scientists do have. 60 minutes, I shouldn't go long, because in 60 minutes we're supposed to get from standing or sitting still here to traveling at the speed of light. So please, Shankar.
Thank you, Adi, and thanks to the Aspen Center for inviting me to give this lecture. I was on this podium 10 years back, at that time to talk about quantum mechanics. And now today to talk about relativity. In most cities, the best way to clear a crowded room, other than shouting fire, is to mention either relativity or quantum mechanics. And yet in Aspen, it seems to have exactly the opposite effects. So I'm very happy to share my understanding of the subject with you. And today is part of what's called No Aspenite Left Behind plan. So you stick with me and you will go places and you will go fast, okay? That's a promise. And one promise that was made and given in writing is that there will be no equations. Okay. All right. So I should start by asking people how old they think the theory of relativity is. And this is for the non-physics people. Anybody want to guess? Would you like to guess? How old? 60. Okay. Any other numbers? 100. Okay. So 100 is a very reasonable guess. But it turns out the correct answer is more like 400. And that is because the relativity principle has been around for that long, and it was made by Galileo. So actually, Einstein is the father of the subject, but Galileo is the grandfather. There's also a godfather, who is Isaac Newton. And I'm going to start by telling you the role they played, and slowly we'll come to Einstein and what he did. All right, so the way to explain all of this is the standard practice is to consider two very long trains. So I'm going to draw the picture of these long trains, and one gamble I'm taking using this board is I'm not sure if you guys in the last row can see what I'm writing, but you must stop me if you cannot see it, okay? All right, here are two infinitely long trains. Now I asked the Aspen Center to give me infinitely long blackboard, but this is all they could do. I'm going to show you a part of those infinitely long trains. So let's call this train 1, and this is train 2. If you like, this is the top view of the train. You're in a station, both of them are parked, and you're looking down. Okay, now you go into this train, and you settle down, and you explore the world around you. That means you can play pool, or you can pour yourself a drink, or if you're a physicist, you reach into your pocket and pull out your mass and spring system. Okay? You attach the spring to the wall and you pull the mass and it vibrates back and forth. That's what I do in the train. So different people have different ways to pass the time. So you do whatever you do to explore the world. Then you look outside through this window here, you see the other train, and on this side is the platform. Okay, now they close the blinds. All the blinds are closed. Now you might say, why are we doing that? It's not because the train is going through certain parts of New Jersey. Okay? We're doing that because we are going to do a serious scientific experiment. The experiment is the following. When the blinds are all drawn, you go to sleep, and you wake up, and I tell you that when you were sleeping, one of two things has been done. One is the train has been left alone. Other is that the train has been given a speed or velocity of 60 miles per hour. The question is, can you tell? Is there anything you can do inside the train to tell you have that velocity? Now you cannot say, I know the train is not moving because it says Amtrak up there. Now, most of the time you will be right, but the laws of physics do permit Amtrak trains to move, though they don't avail themselves of that possibility. So you cannot use sociological reasons. The question is, can you do anything involving physics that will expose your motion to you? And the principle of Galileo is that you cannot. You cannot. And you notice that whenever you go in a plane, if it's not very bumpy, you are not aware of the large velocity of the plane. And even in a train, if it's going very smoothly, you will not be aware of its velocity. So Galileo made this observation that if the train has a certain constant velocity, that means it should go in a straight line at the same speed. If it swerves from left to right or bumps up and down, you will know that you're in a moving train. The question is, if it doesn't do any of that, will you know you're in a moving train? And Galileo said, you will not know. Now, where is the relative in relativity? I have not said that yet. That comes about when you open this window, say this side, and look at the other train. Suppose you find the other train is moving this way at 60 miles an hour. Can you tell who is actually moving? And the claim is you cannot. In fact, if these are the only two things in the universe and they're sliding past each other, there is no way you will know whether you're going this way or the other train is going that way or some combination of the two. So that you will admit there is motion between the two of you, and that's relative velocity, but there's nothing absolute in the sense that there's nothing inside your system that will betray your velocity. That's why you don't know about it. But you should be very, very careful that it's only uniform velocity that you are not aware of. For example, if the engine driver slams the brake and you slam into the seat in front, you lose all your teeth, and at the moment the blinds fly open and you see this fellow here on the other train. Can you tell that person, nothing is happening to me, I'm at rest, but you're accelerating in the opposite direction? You cannot say that. First of all, you cannot say anything because you lost all your teeth. But suppose you write in a piece of paper and say, hey, I'm not moving, you're moving the other way. He will say, how come you got no teeth? Nothing has happened to me. Right? So acceleration produces effects. You cannot talk your way out of acceleration because things happen in your train that don't happen when it's not accelerating. So it is not true that all motion is relative. Accelerated motion produces effects, and you don't have to look outside to know you're accelerating or decelerating. But as long as the velocity is uniform, you will not know. That's what Galileo said. That is the principle of relativity, that a person in a closed train is not aware of his or her velocity. That's it. If you go home now, you still know what relativity principle is. In fact, you will know that you have known it all your life. So the real question is, what am I going to do for the rest of the time? I wish Adi's introduction was longer because that is the principle, folks. It's not changed. No, just settle down. He cannot resist the microphone, so I got to keep him under check. No, I'm not. It's not time for him yet. But he's going to enter this later on. You watch. Okay. Anyway, Galileo said uniform velocity cannot be detected. Acceleration can be. It can be felt. That's it. And we all know that. So then we come to Newton. So what Newton did, Newton's life started pretty much when Galileo's ended. What Newton did was to prove the principle of relativity. Now, what does that mean? So he wrote down his 3 laws of motion, and he could prove that if the laws of motion were valid in the train when it was on the platform, they will continue to be valid when the train is moving at any fixed velocity. They won't be changing. The fact that the laws don't change is what makes you think you're not aware of your motion. You're not aware of your motion because the laws have not changed. So there are 3 laws of Newton. So I'm going to talk about only the first one because the second one is an equation. Now, something, right, equals something else, not allowed to say that because I've been told that when you bring up equations in these talks, half the audience will leave, other half will storm the stage and attack the speaker. Another story I heard is that Pepke was redesigned so that the minute I write an equation, this floor will open, fall into a pit full of sharks or snakes. So we will not use the 2 equations of 2 laws of Newton, second and third. We'll talk about the first. That's good enough. First law of Newton's good enough. The first law says, if you take something and you leave it somewhere and there are no forces on it, it will stay wherever you left it, like this guy here. If that law is valid for you, the law of inertia is valid. It also says something slightly less intuitive, which is that if something has a constant velocity to begin with, it will maintain that velocity for free without any forces on it. Basically, if there are no forces on a body, it won't change its velocity. If it was 0, it will remain 0. If it was 60, it will remain 60. That's called the law of inertia. And if the law of inertia is true for you, then you're called an inertial observer. So we are inertial because here it is, I leave it there and it stays there. Now you got to be a little careful because When I said this earlier on, somebody said, I went to Grand Central Station and I left my iPod and I came back and it was gone. So I had to tell the person the laws that are broken have nothing to do with Newton. New York City laws that were broken. I'm sure there was some unseen hand that came and applied the necessary force. So the Earth is pretty good approximation inertial frame because things stay where you leave them. All right, so one of the laws of Newton is the law of inertia. What I'm going to explain to you is that if the law of inertia is valid for a guy in the platform, it's also going to be valid in the train moving at 60 miles an hour. So let's see how you show that. So here's the train. This is the side view of the train now. It's running along, and that's a huge glass window, so I can see what's happening inside the train. So inside the train, let me make this bigger. Okay, here is the train, and there's a guy sitting inside the train. Okay, my artwork is a source of constant amusement to my students, so you can have the same treat. So here is some guy, and there is a jug of beer he has put on a frictionless table, okay? And the beer is going at 60 miles an hour, he's going at 60, the whole train is going at 60. The question is, will the person in the train find the law of inertia is valid or not? Namely, will the first law of Newton be valid in a moving train? I'm saying I can prove that it will be valid. Here is how you prove it. You don't know anything about the guy, but you can look inside the train, and you're allowed to use Newton's laws because you're still on the platform. I already told you the Earth is a pretty good inertial frame. So what do you find in the beginning is that there's a guy going at 60 miles per hour, there's a jug of beer going at 60 miles an hour. The beer is on a frictionless table, so there are no forces acting on it. So it'll keep going at 60. The train, I've been told, is going at 60. Therefore, they're both going at the same speed. That means the distance between them will not change. Two objects going at the same speed will maintain the same distance. Therefore, I conclude that this fellow will notice the beer stays put. So that's the first part of the inertia law, that if you leave something, it'll stay there. So it stays there, not because I know that he will find Newtonian laws in his train, because I know I will from outside. And from that I predict that the beer and the guy will go at the same speed. And now suppose he gives this beer a shove and it starts going at 70 miles an hour. What will happen next? I know the beer will keep going at 70 because there are no forces on it, as seen from the ground. He is always going at 60. So I know that from his point of view, he'll be going at a speed of 10. So he will find if it starts out at 10, it'll maintain the 10. So he will find the law, first law of Newton is valid for him. Similarly, you can prove that the other laws are valid. So if the laws are the same, the world will look the same. That's what it means for the world to look the same. But suppose the train accelerates, then what will happen? If the train accelerates and this beer is going at 60, let's go back to the old example. If the train accelerates, this guy is picking up speed, but the beer is going at the same speed because there are no forces on it. So soon he will catch up with that beer, he will collide. But in the train, it will look as if the beer slid towards him and hit him. So this is something you experience in a plane, right? When the plane is taking off, what happens? You're accelerating, and everything slides to the back of the plane. Not everything that's not nailed down goes to the back of the plane. That's why all the physicists are sitting in the last row collecting the stuff, okay? And when you land, everything goes to the front of the plane, and we are there too. So that's what we mean by economy plus, okay? That's the plus. So we are collecting stuff because we know the laws of Newton. So when you're in an accelerating train, there's no trouble realizing you're accelerating, okay? Because things happen. So that is not an inertial frame. Things don't stay where you left them in an accelerating frame. They slide back, or they slide forward, or they fly off to the side. So Newton's laws are not valid in an accelerating train, but they are valid in the train going at a constant velocity relative to the ground. So let me summarize. Galileo simply observed that we are not able to detect our velocity in the train without looking outside. Newton proved it had to be so because he said, here are my three laws, and they don't change when you go on a moving train. Therefore, in a moving train, nothing will betray your motion. That's it. That's the story of relativity till end of Newton's time. Now you will notice that I've been talking about the subject without mentioning one entity that plays a major role. Do you know what I'm talking about? Hasn't entered the picture yet? This is for, pardon me? Light. I've not mentioned light so far, so it's going to enter now. So people have been thinking about the velocity of light for a long time. It was not even clear that it travels at a finite velocity. So different people have had different things to say. Alfred E. Newman said, this is what I know about the velocity of light. It gets here too early in the morning. Now, Galileo made his own comments about the velocity of light, and this is what he did. He tried to find the velocity of light as follows. He went on top of one mountain, and his friend went on top of another mountain, and they both had, this is Galileo, this is the friend. They both had lanterns which could be closed, like a shutter. And if you open the shutter, the flash of light comes. So Galileo told his friend, I'll open my shutter, and the light will come from me to you. And when you see that, you open your shutter, and the light will come back to me, and I'll see how long it took, right? And I'll divide by the time, I'll get the velocity. So he got some velocity, but then, being a smart guy, he repeated the experiment and noticed that the time of travel was independent of where the two mountains were. Even if you went to that mountain, it took the same time. Then it became clear that what he was measuring is the time of response, not really the travel time. Now we know that he had no chance because, as you know, light can go around the world about 7 times in 1 second, and here you are trying to go as a distance of a few miles, and no human can measure that time. So the first person to really have a good crack at the velocity of light was an astronomer called Romer, and I will tell you what he did. You see, light goes so fast, there is no way of measuring it in the laboratory. Nowadays you can, but not in those days. So his trick was very clever. So I'll take a minute to tell you what his idea was. Okay, so here is the sun. And here is the earth. And here is Jupiter. And Jupiter has a moon that goes round and round. Okay? So that moon is called Io. And it's got an orbital period, which I don't remember. Let's say it's 1 hour. So every hour, this moon goes around and comes back. And you see it from the earth. So you make a little plot. Every time the moon comes right in front of you, or right in front of a certain part of Jupiter, you make a little mark and say, I saw the moon. Then you wait an hour, you see the moon again. But what he noticed is that after a while, the blip that's supposed to arrive like that came a little later. So there was a delay. The blips were not coming on the hour. First it was half a minute late, maybe 1 minute late, then 2 minutes late, and later. And the explanation was that while he's doing all this, the Earth is going around the sun, and by the time you come to the other end of the orbit, in the simple argument, I'm going to assume Jupiter has hardly moved, so let's not worry about that. You can see it's taking longer and longer because the first one, the light came like that. For the one that came really late, light had to cross the whole solar system. So people had some idea how big that was. Not the solar system, I'm sorry, double the radius of the Earth's orbit. And once you have something like 93 million miles times 2, the delay is several minutes. I forgot what it is, 15, 20 minutes. Then from that he extracted the velocity of light. The velocity he got was 200,000 kilometers per second. And the correct answer is more like 300,000 kilometers per second. But it was a very good measurement. A factor of 2 is fine in this kind of problem, and it was the first real measurement of the velocity of light. And since then, people managed to do laboratory experiments, very clever experiments with rotating mirrors and whatnot, that got the answer to be close to what we know today, which is 300,000 kilometers per second. All right, so this is what was known about the velocity of light. But nothing much was known about light. What is it? We don't know. We just know that you turn the switch, you see it. That's all people knew. So the next significant experiment about light was done by Young. So Young was an English physicist, and he showed that light is a wave. I got to tell you what it means to say something is a wave, because waves have a very distinct property that betrays them. They do something that nobody else can do. So I'm going to give an illustration of what we mean. So here is a marina. This is the ocean, and this is the land, and this part on the beach is your yacht. See, I brought this example just for people in Aspen so they can relate to what I'm talking about. Okay? So here's your yacht, and you're just trying to get some rest. Okay? But what happens is the ocean waves come and slam into your yacht, and you're upset by that. So what you do is you immediately have a big wall built. You build a wall, now everything is fine. But one day, something happens to the wall, and there's a breach. When you have a breach in the wall, of course, these waves start coming, and they hit your yacht. And once again, things are bad. Things are rocking up and down. And the question is, what should you do? Well, one option is to fill up this hole. Suppose you don't have the materials, and all you have is a sledgehammer. I'm telling you that's a solution to your problem. The solution is, if these waves, assuming they have a definite wavelength, you can make another hole somewhere here. And that will send more waves, and they will come to you, and you can arrange it so that the signal from here is exactly canceled by the signal from here. The way you can do that is between these crests in the water, and also these troughs in the water. So when the wave comes here, it tells the boat to go up and down and up and down, and this signal is delayed by a certain amount so that when this one says go up, that will say go down. A little later, that one says go down, this will say go up. The two signals can actually cancel. That's called interference. But of course, there are other locations where they will add, where the up and up from the two holes will come at the same time. The water is going to be very rocky. That's where your neighbor's yacht is parked. And you don't give a damn. That's his problem. Okay? So let him make another hole. Anyway, that is interference. Okay? Only waves can do that. See, waves have the remarkable property that if you open a second opening, naively you might think things are going to get worse, but they can actually get better. Only waves can do that. Okay, for example, if there's mosquitoes coming through a hole in the wall, don't try to make a second hole. It's going to get worse, okay? Because mosquitoes are particles, but waves have the property they can neutralize each other. All right. So what Mr. Young did was to do essentially the same experiment, except this was a screen in the back of the room, and that's a source of light here emitting some, well, I shouldn't say waves because we don't know it's waves, but what you do is you make two holes. And you look at the screen behind and look at the pattern of bright and dark. And what you find is right in front, right in the middle of this thing, is a very bright region. Then there's a dark region, then there's another bright region, another dark region. These patterns of bright and dark tells you it's waves. And if you know the spacing between these, and you know the spacing between the holes, you need to know that distance, you can find the wavelength of light. So he was able to find the wavelength, and he was able to show it's a wave, but it was not clear to them what it is that's waving. In water, we know the water is going up and down. In sound, you know that when I'm talking to you, my diaphragm moves back and forth, and the air molecules move back and forth, and they come to your eardrum, shake your eardrum. After that, that's for the biology department. So I check out right at the eardrum. There's a lot of hairs moving around, and the signal goes to your brain. But at least this part, we know what happens. So what's changing there is the air pressure. You can also have interference with sound waves, but it is not clear in the case of light exactly what's going on. Something has got a wavelength, but we don't know what the something is. That's all Young could do. So I'm almost ready for the main character, who's Einstein. I got to mention one more guy called Maxwell. Because unless you go through the history, you will not know what the problem was at that time. So Maxwell was studying electromagnetism. Now, you are all familiar with electricity and magnetism, right? If you walk on a carpet, then you touch the doorknob with your key, you see a little spark. That's electricity. Magnetism has been known from ancient times. In fact, parents in ancient Greece noticed that the kids were sticking things on the refrigerator using little black rocks. So they've been knowing about magnetism for a long time. Anyway, that is electricity and magnetism. And people knew about something called electromagnetic fields. In fact, right now, at this point in space, I'm pretty sure there is an electromagnetic field. What does that mean? It means if I take a charge like proton and put it there, it won't stay still. It'll either try to move up or down or from side to side because it's an electric field. And the direction in which it tries to move is the direction of the electric field. And how hard you got to work to keep it where it is the strength of the electric field. And similarly, if you take a compass needle, it'll line up with the magnetic field. In fact, the Earth's magnetic field, we know, is everywhere. That's what lines up the compass. So a field is present everywhere. These are called electric and magnetic fields. What Maxwell showed is that these fields can be found on their own far from all electric charges and electric currents that produce them. And they travel in the form of waves. In other words, when a wave travels, you draw a picture like this with your hand, but what does up and down mean? For water, we know what it means. Here the water is up, here the water is down, here the water is up. When you do electromagnetic waves, you mean here the electric field is strong, and here the electric field is zero. Here the field is strong but pointing the opposite way. That's called electromagnetic waves. There's an electric field and a magnetic field. In fact, the way it works is if you have your 3 fingers here, that's the electric field, that's the magnetic field, that's the direction in which it moves. That's another formula in physics. So you can see many people who didn't make it in physics went into rock music, and this is what they're doing. See? If you don't follow the lyrics, they're really using what we call the right-hand rule and left-hand rule. That's one of our major contributions to rock music. Anyway, you should remember this, electromagnetic field. All right. So Maxwell was able to calculate the speed of these waves. He put in the numbers coming from electric and magnetic measurements, and he got an answer that is remarkably close to the velocity of light. And everybody said that means light is just electromagnetic waves. You got to be a little careful, right? The velocity being equal doesn't mean they're the same thing. Suppose I'm walking in the street and Brad Pitt starts walking next to me at the same speed. No matter how much he wants, he's not going to be me. Okay? So velocities being equal doesn't mean anything. But this time they were right. It is in fact, electromagnetic waves are in fact light. So then the question was, in what medium is this light moving? Because every wave has a medium. Sound waves have a medium, which is air, and water waves have a medium, which is water. Waves on a string have a medium, which is the rope, a string on which it moves. So they didn't know what this medium is. So they gave it a name, and the name was called ether. And where is this ether? They figured it's everywhere. It's all the way from here to distant stars. That has to be ether. So think about why. Because if you didn't have the ether, you won't be able to see the stars. The fact you can see them means this marvelous medium that carries light waves is everywhere. Good. That was just fine. Then the speed he calculated is the speed with respect to that medium. For example, the speed of sound is whatever, 340 meters per second with respect to the air. And if you start moving along with the sound wave, it'll appear slower to you because you're moving with respect to air. But if you carry the medium with you, the wave will travel at that speed. So what people said is, let's find out how fast we are moving this instant with respect to this ether. And they reasoned as follows. They said, Maxwell has given the speed of waves. It must be in the ether. If we are moving along the direction of light, then the speed of light will be reduced as seen by us. So let's measure the speed, and from the difference, we'll find out how fast we are moving today. When they did the calculation, when they did the measurement, they got exactly the speed he calculated, 3 times whatever, 300,000 kilometers per second. The only conclusion you can draw is that at this one instant, when I did my experiment, by luck, I happened to be at rest with respect to this ether. But that luck will not last, you see. You're sitting on this rotating planet, and the planet's rotating. If you're here today, you're moving like this. 12 hours later, you're moving the opposite way. You cannot be at rest both times, but what you find is the velocity of light is the same. Morning, noon, nighttime, anytime, you get the same answer. Then you say, let me wait 6 months till I've gone to the other part of my orbit. Then I'm also moving at a different speed. There also you find the velocity of light is the same. So this was what was very puzzling. The velocity of light came out to be the same no matter who was looking at it. So one theory was, when you're on the Earth, maybe the Earth is taking ether along with it. For example, there is air all around us. We are traveling through space at a very high speed, but we don't feel it because the air is coming with us. Right? So when I talk to you, I don't have to worry about the fact the whole planet is moving because the air on which sound travels is traveling with us. Likewise, when I go to a plane, I'm sitting on the ground, there is the air. I call the stewardess, can I have a pillow? It takes her about 3 microseconds to pretend she didn't hear me. Okay. Then I go in the plane at 600 miles an hour, ask for the pillow, takes her the same time to ignore me. Okay. That's because I'm taking the sound, I'm taking the medium with me. Then it's not a mystery that the speed is independent of the speed of the plane. You're taking it with you. But you can show you cannot take the ether with you. That'll take care of this problem, but when you look at stars, you can show that the ether is not being carried with you. So here is the problem people have. I want you all to understand that. Light has this peculiar property that its speed is independent of who is measuring it. That's very surprising. It doesn't make any sense because the speed of objects should be dependent on who's looking. Especially people moving along with it should think it's going slower. People going against it should think it's going faster. But that's not what happens. And no model of the ether was able to explain this. Now you're ready for Einstein. So this is when Einstein enters the stage. So he said, I know what's going on. He said, I know why light does this funny thing. He said, remember Galileo's train? You went in, you closed the blinds, you did all kinds of experiments, and when you woke up, everything looks the same. But suppose the velocity of light depended on how fast the train is moving. Then you'll get a different answer when you wake up. And from that difference, you can infer your speed. But that would mean the laws of relativity, the principle of relativity that says you cannot detect your own motion, is valid for mechanics, but not valid for optics and electromagnetism. That's like saying in your physics book, the first 10 chapters, which usually deal with mechanics, have laws that look the same in a moving train, but optics and everything else looks different in a moving train. So Einstein didn't believe in that. He said either the laws are the same or not the same. It doesn't depend on which chapter of the book I'm reading. So he said, I believe more in the principle that you should not be able to detect your velocity using any phenomenon. So he went on to say, light is part of the conspiracy to prevent you from detecting your motion, and all phenomena, whether it's in mechanics or electricity or biology, everything, they should all behave exactly the same in a moving train, as long as it's going at constant velocity. If even one of them, say rats behave differently in a moving train, then you can look at your rats. Hey, they're not going through the maze the way they used to. I know the train is moving. But I claim that if it's going at constant speed, the rats will behave exactly the same way. So all phenomena, whatever their basis, should look the same. That was his principle of relativity. That's what he said. So he said the principle of Galileo was threatened by light, because if the velocity of light was different for each person, then they can find their own speed. But they are not able to do it, so the principle of relativity is safe. That's what he said. That was his main theory. Now you can say, what, that's it? That's all the guy said? Did he do anything else? And the answer is, he did a lot. Because when you say the velocity of light is the same for everybody, you are setting yourself up for a lot of problems. A lot of weird things are going to happen to you. And he took all of them, because he was going to save the principle. He was going to throw Newtonian spacetime under the bus. Notice I didn't say abandon Newtonian spacetime. I said under the bus, because this is a talk about planes, trains, and automobiles. And I've had my plane and my train. The bus is the closest thing to an automobile I can work into my talk. Okay, so anyway, he abandoned everything. But I'm going to tell you what happens once you accept the velocity of light is a constant. I want you to think about the following situation. So you're on the ground, and there is some car going past you, again at 60 mph. Imagine now some other guy gets on a motorbike and follows this, and he's going at 40 mph. Our expectation is that this guy will think the car is going at 60 minus 40 equal to 20. That's just a fact. And if he's going exactly at 60, he will think this is not moving. If he's going at 70, he will think it's moving backwards. So the rule is, if something is moving, and it has a speed as measured from the ground, and you move, you should subtract your own speed from that speed to figure out what you will see. And that's confirmed in daily life. Things look slower when we start traveling the same direction. But the claim is, if instead of being an automobile, it was a pulse of light, namely open and close a shutter, and a pulse of light is emitted and starts traveling, and the people on the ground think it's traveling at a speed c, and you go in a train that's going at a speed, let's say 3/4 of c. What do I expect? I expect you to get a velocity of 1/4 of c, because you got to take away your 3/4. But it's an empirical fact that even a person going at 3/4 the speed of light will look at the same pulse of light and attribute to it a velocity c. It does not slow down, even if you move in the same direction. So that is the mess you get into. You have to accept that. But how is that going to work out? What has to be sacrificed is the following. Let's think about it. I'm on the ground. I get a speed c. You're going at 3/4 of c. I expect you to get 1/4 of c, but you get 4 times the answer. So what will I think is happening? I will say this person's measurements are flawed, because velocity is distance over time. Maybe your clock is running slow. If your clock is running exactly 1/4 as slow, at 1/4 the speed, when light has traveled for 4 seconds, you may think it's traveled for only 1 second. So when you divide by the time, you'll divide by a small number and get a bigger speed. Another possibility is that the meter sticks you use to measure distance have become shorter. So when light has traveled 1 meter, you think it's traveled 4 meters. Then you exaggerate the answer, you get 4 times the answer. Maybe both are happening, but something has to change. That is the whole point. So what Einstein did was figure out what are the things that happen. So I'm going to tell you qualitatively some of the consequences of this principle. I'm going to talk mainly about time because that's more easier to talk about and easier to visualize. So let's take these postulates that Einstein made and deduce whatever he deduced. And you'll see the deductions are pretty amazing. And one of the great things about Einstein was not simply his intelligence, but also the courage he had to stand by all the crazy things that followed. So physics is partly about being smart and partly about being courageous, because when you say something very dramatic, you got to stand by your theory and go wherever it takes you. And you will find that the simple statement that the velocity of light is the same for everybody takes you to all kinds of interesting places. So here is the first thing that follows from that. So imagine a pair of twins. Okay, one is born in New York, one is born in Los Angeles. Okay, so when I gave this example in my class, people pointed out that it's no ordinary mother who can give rise to. It's the mother from the Yo Mama jokes. She's so big she could have kids on coast to coast. Anyway, imagine 2 events, okay, not twins. 2 events, one takes place in LA, one takes place in New York. And they take place at the same time. Now, we are smart enough to know that same time doesn't mean the clocks will read the same. It can be 12 o'clock here and 3 o'clock there, but we know in our guts what it means to say they happened at the same time. And in Newtonian physics, that notion is absolute. In other words, if 2 things happen at the same time in 2 parts of the country, everybody will agree they happen at the same time. Even a person in a plane or a jet or a rocket, the fact that they're happening at the same time is true for everybody. But you can show that that's not going to be true in this new theory. And this is how you do that. So again, you go back to this train. And you're in this train. And you want to have 2 things happen at the same time, at the 2 ends of the train. You have to engineer it somehow so that it happens. So what you do is, you take 2 mirrors, with, say, some angle between them, and you send a pulse of light, it goes there, and one branch splits this way, and one splits that way, and goes to the other end of the train. And if you're sitting right in the middle, you can see that the light signal will reach the two ends at exactly the same time. Let us say they trigger some explosion. And the explosions will be simultaneous. That's the best you can do, and that's your definition of simultaneous. And the question is, what will I think if I'm sitting on the ground, and according to me, you're going at some speed? Will I think they're simultaneous? And the answer is, I will not. Because I argue as follows. This pulse goes to the right at speed c, but this end of the train is running away from it. This pulse goes to the left at speed c, and this end of the train is rushing to meet it. It's very clear that this wall, the light will hit this back wall first, and somewhat later it'll hit the front wall. Do you follow that? Therefore, they are not simultaneous. They're simultaneous for the person on the train, but I think they're not simultaneous. Now you might say, why are you using a light signal? What if you send a couple of pigeons? You release 2 pigeons, they go. But the point is, we don't know enough about pigeons, okay? Or 2 Federal Express guys, okay? Send 2 FedEx guys. What do I know? I know they will absolutely positively get there by 10 o'clock, but I don't know if they will get there at the same time, okay? So you don't want to use anything because all the old rules are off. The only thing you really believe in this new crazy world is the velocity of light is going to be the same, no matter who emits it, no matter who sees it. Therefore, the fact that this is emitted by a forward-moving train, it doesn't matter. This will go at the speed c. I know that will go at the speed c. Then there is not much that can go wrong with the argument. If it's going at the same speed in 2 directions, and one end of the train is going towards the pulse, one end is going away, you can easily tell they won't be simultaneous. Therefore, the person on the ground will say, this happened first, that happened later. And you can find another person, in fact, in a train going twice as fast, to whom this train is going the other direction. He will say that occurred first and this occurred later. So the same 2 events are simultaneous for one person, or A occurred before B for another person, or B occurred before A for another person. The order of events is negotiable. Now, if you were Einstein and you realize this is what your theory is saying, you will realize you got a serious problem in your hands, right? Because the order of events is pretty sacred. For example, event number 1, my father is born. Event number 2, I am born, okay? We think that the first event occurs first and the second is my birth. What if there is some guy going in some rocket for whom I am born, my father is not born yet, okay? That's very difficult situation to be in, right? They got this cute little baby in the hospital, and they say, what did we name this kid? And they say, the father is not here yet. So, you see, caught in traffic? No, he's not even born. Now, what's wrong with that picture is that since I have been born, my father is not yet born, something can happen to him as a result of which he cannot have kids. So it's hard to explain my presence. I'm going to give another example that you can all relate to. Suppose I realize that Adi's introduction was not flattering enough. So I take a gun and shoot poor Adi, okay? Pow. So event A is I fire, event B, Adi bites the dust. Now what if there's some observer for whom Adi's been hit the floor first and I haven't shot yet? Then somebody comes and grabs my hand and takes away the gun, so he's been killed for no reason. We know that cannot happen. You're all laughing because that's not allowed. And yet we know the theory allows you to fool around with the order of time events, right? So how can you avoid such situations? If you ask yourself, what is it about this pair of events that made it absurd to reverse their order? It is that one event was the cause of the second event. I fired the gun, my friend took the hit. They are the 2 events where this is the cause of that. If one event is the cause of another one, you never want anyone seeing them in the reverse order. Because if the effect comes first and the cause has not occurred, someone can interrupt the cause, then you would have a universe in which you have an effect with no cause. So that's logically dissatisfying. So somehow the theory should be able to allow certain events to have an order that's same for everybody, whereas in other events it doesn't care. Now, Einstein doesn't know the scenario behind every pair of events. So how is he going to tell you what's allowed and what's not allowed? And the theory has a very beautiful resolution. It says if this is the first event, occurs here at this time, that the second event occurs there at another time. If there is enough time for a light signal to go from this event and arrive in time at that event, then this event could, in principle, have been the cause of that event. Then their order is sacred, cannot be reversed. In the example of Adi and me, the time between the two events is the time it took a bullet to go from here to there. That's certainly enough time for a light signal to go from here to there. Those events cannot be altered. But if there was no time even for a light signal to go from the first event to the second event, the theory argues that the first event could not have been the cause, because nothing can travel faster than light. The first event could not have affected the second event. In those cases, theory plays fast and loose with the order of events. You will find you can switch them around, but there will be no contradiction. So when you have the right theory, everything works out. It's really amazing when you have when you're on the right path. A lot of paradoxes arise, but in the end they get resolved. So I'm going to tell you one other thing involving light, which is the behavior of time. So first thing about time I've showed you is that simultaneity is not absolute, and the order of events is not absolute. Very often the order of events can be reversed depending on who's looking at it. Next thing has to do with the behavior of time itself. And the claim in relativity is that if you have a clock and it's ticking out 1 second, and if the clock begins to move, according to me, I'll claim that the clock is running slow. In other words, every clock will run the fastest in the frame in which it is sitting. If it's moving according to any observer, that person will say the clock is running slow. Now, how am I going to explain that to you? Because, first of all, I don't know how any of these clocks work, especially this clock. I have no idea what's inside. So what we're going to do is we're going to take a clock whose mechanism is very simple, where we can actually follow how it works. Then we will see right away why it slows down. So this is a clock where you get a pair of mirrors like that, and you have a light pulse that goes bouncing back and forth between the two. And every time it makes a round trip, it hits something and it goes click. That's your clock. So you go buy another clock just like mine, and you make sure that it's got exactly the same height, and we start them off, and they will be going tick, 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 completely in synchrony with each other. Very good. Now you get into the train, and you move past me in this train, and I look at your clock, and I find your clock is actually doing this. You agree? Your clock, the path that looks up and down, is a zigzag path. For example, if you go to a train and throw a ball up and catch it, it's up and down in the train, but from the point of view of the ground, it is a zigzag. Goes up and comes down like that. Now it's very clear that going like this, up and down, is longer than going like that. Because one is the hypotenuse, one is the vertical side is longer, but the speed of light is the same. So longer path simply means longer time. That's once again where you appeal to the fact the speed of light is one thing you know. Therefore, you may conclude that this clock, which is moving to the right, will run slower than this clock, which is sitting here, ticking much faster. Therefore, the world is divided into people who think the clock is running at the correct rate and all the others whose clocks are supposed to be slow. But the only fault of this person is that he's moving relative to you at some speed, but we have argued that that person has every right to say, I'm not moving, you're the one who's moving. So why should this clock slow down? In fact, if he looks at you, what will he find? Well, I don't have room in the blackboard, but he will think the other clock is going the opposite way. You understand that? The clock is going straight up and down only for one person. For anybody else, it's going zigzag. So everybody else will think the clock is slow. But the beauty is, I can say your clock is slow, you can say my clock is slow. Completely legitimate. Then the question is, when we meet, what's going to happen? How are we going to resolve this? After all, if I say you're slow and you agree you're slow, that's no problem. But if I say you're slow, like kids, you're stupid. No, you're stupid. When you compare these two stupid kids, who's going to be really stupid? That's what we want to do with these two clocks. Who is really slow? The point is, as long as these clocks are moving in opposite directions, you're never going to get to compare them. So you will never have a paradox. Better example is given with human beings. You got the same twins. Now one twin is sitting here, other twin gets into some rocket and goes around for a long orbit and comes back. So the twin on the Earth tells the guy in the rocket, you went on the trip, so you are yourself a clock, and therefore you will be running slower. Do you understand that? Not only mechanical clocks, human beings are biological clocks. They will also slow down. Because if a biological clock did not slow down, whereas this clock slowed down, then a person in the moving train can compare the two clocks, and by noticing they're different, will know he's moving. So all clocks will run at the same rate in the train. For this clock, I can see why it looks slow, but if there's any other mechanical clock, it will run at the same rate. When this goes tick and that goes tick, a little later both will go tick. So every clock will slow down. So human beings are also clocks, right? If you had enough time, if it was a lecture of 60 years instead of 60 minutes, you can just sit there and watch me get old, okay? My teeth will fall off, my hair will fall off, everything will fall off. That's the measure of time. So humans and everything else, living things measure time, and they will also slow down. So if you take these two twins and one goes on an orbit, comes back, the twin, being a clock whose heart beats at a certain rate, would have beaten fewer times and will come younger than the person who never left. But what about saying the argument backwards, and the kid in the rocket says, I didn't go anywhere, you went the opposite way, then I should be younger than you. So when they meet, who will be younger? And the answer is the person who went on the rocket and came back will actually be younger. The reason he cannot claim equality with the person on the ground is that in a rocket, you went away from me, you accelerated away from me, you turned around, again you decelerated, you sped up and came back, you slowed down and stopped. You've done a lot of acceleration. During that acceleration, you felt the G-forces, you're throwing up. It's very clear you did all the traveling. Whereas I was here, I was inertial the whole time. That's why you cannot say you're equal to me. So in the twin paradox, the one who went on the trip will be younger. So take a mirror and hold it in front of your face, and if you like what you see, I'm going to give you a plan for keeping it the way it is. Okay? The plan is to get into a rocket and go at a very large velocity. And you stop aging. You cannot go back in time. So you're stuck with the face you got. But you can hang on to it. That's what I'm saying. Go on an orbit as long as you want. If you're waiting for Mr. Right or Mrs. Right, you tell the people on Earth to give you a call when somebody reasonable shows up, then you can come back. So you can essentially halt the flow of time by going fast. That's not science fiction. That really is science, because in all these colliders, they're producing particles which are not supposed to live very long according to themselves, but they're produced at such high velocities that they live much longer, and that's when we get time to observe them. Okay, so the consequence of the slowing down of time is that particles, which should have died very quickly, live very long. There are particles produced in the upper atmosphere, which really shouldn't make it all the way down because they don't live that long enough. But because they're traveling at high speeds, they live longer. So you've got to remember that. The biological clock slows down. Anything that moves will slow down. It also means something else for space travel. How much of the universe can I explore? You might say, look, you just told me the limit is the velocity of light, and you're probably going to live 100 years. So maybe you can go 50 light years and come back in another 50 and brag about your trip. So maybe the exploration is 100 light years. That's actually wrong, because the minute you travel at very high speeds, you don't age at all. So you can go for 100,000 Earth years and come back another 100,000 Earth years. You can age by just 1 second. Except you won't have anybody to talk to when you come back, because all your classmates would have died by then. Okay, but you can go as far in the universe as you like. So even though the velocity of light is a limit, it doesn't limit the distance to which people can travel. Okay, so I'm not going to say too much more about the various consequences, because some of them are harder to follow. One is that a meter stick, when it moves, will appear short to you. It is really short in a very real sense. For all practical purposes, it is short. It can be 1 meter long when it's at rest. When it's going fast enough, it can be half a meter long or 1/10 of a meter long. So fast-moving objects will behave like short objects to you. So here's one example. You have a barn, and you want to throw a party for 500 people. You can only fit 10 in the barn. So you put them in a fast train, and you speed up the train so that when they pass through your barn at the high speed, all 500 of them fit into the barn. Okay? It's going to be a very short party because you're going at very high speed. But you can pull it off. Okay? So these are real things. These are things that actually are not of practical use, but these are real things. When things move, they contract. That's somewhat harder to follow, and not only that, I will say your meter sticks are short, and you will say my meter sticks are short. How are we both right? They are things that one should read about. But what I wanted to do today is to simply say a few things which you can follow and have an intuitive feeling for. But what happens is bizarre, and it's not any less bizarre for me. The fact that things slow down when they move is very strange. I'm not used to that either. By working with it for years, we think we are comfortable with them, but they are very strange. And I wanted to communicate to you the strange consequences of the principle of relativity. So I'm going to summarize what I said in 1 or 2 minutes. So Galileo noticed that when you go into a train and close all the blinds and the train has a certain velocity, you cannot realize it. Nothing betrays it. Newton said, I explain all phenomena with my 3 laws of mechanics. They don't change when you go to a moving train. That's the explanation of what Galileo said. Then the velocity of light behaved in a strange way that people didn't understand. And Einstein said, that's part of the conspiracy to hide your motion. If the speed of light varied in the moving train, you can find out how fast you're moving. But the principle of relativity says you cannot do that. That's why light behaves that way. But the minute you accept that the speed of light is the same for everybody, you know that length and time cannot have the same interpretation as before. So what Einstein did was actually ask, how do we measure length? How do we measure time? How do we make things simultaneous? And using the constancy of velocity of light, one is able to show that simultaneity is relative. One is able to show that clocks slow down. You can also show that rods will shrink, and you can do all kinds of other stuff. Finally, you listen to me for 1 hour, and I've not told you about the formula, right? Now, the reason is, first of all, I'm not allowed to use formulas. Secondly, it is not easy to explain that formula the way it is to explain this. But that's something I invite you to do at your own leisure. Thank you very much. Okay, do you want to moderate the question period? Okay, so I'll be happy to answer any questions you guys have. Yes?
Did you say the velocity of light will take you to interesting places? How did you?
No, the question was, velocity of light will take you to interesting places. What I meant is, in an intellectual journey, not to any real place. Okay? All right.
Is that how you said it?
That's what I meant, yes. Yes, sir.
This lack of intuitive ability to understand why this works, is that related all to the concept of space?
Yes, this is the space-time. Our notion of space and time at the time of Newton was that there is one time for everybody. And there is something called now, there's something called later, there's something called earlier. That's it. All people agreed on that. In the new world, what is now for me is not now for everybody else. 2 things that occur at the same time for me are not at the same time for someone else. Right? They can say this occurred earlier, that occurred later. So space-time has a different structure now. The notion of simultaneity is also gone. And length was supposed to be absolute, right? What's the length of a rod got to do with how fast it's moving? And yet it does. What is the length of a clock? How come your age is affected by going on a plane? It should not be affected. And one reason we don't feel that is that you go on real planes, even though it looks like you spend years and years on the plane, really your life is not any longer, it's just more miserable. Because there are very tiny effects of moving, but they depend on your velocity to the velocity of light squared. That's a very tiny number, so we're not aware of it. Had we been moving at large velocities, many of these things would have been aware. We've been aware of that. So kids will be aware that things are not simultaneous for everybody. You'll say, I'll see you there at 6 o'clock, you go at 7 o'clock, and you will know that it doesn't mean anything. I should tell you one thing. If 2 things take place at the same time, at the same place, that is same time and same place for everybody. For example, 2 cars come and collide, they're at the same place at the same time. You cannot find another observer for whom it's different, because that person will say the cars did not collide. That's not what we mean by the world looks different. Things collide, they collide for everyone.
You said that they couldn't find a meaning in light.
Yes.
And you also said that light is the same for everyone, that
No.
Why couldn't medium for light be time?
No. I said people used to think time is the same for everyone. But now we realize that it depends on the person's point of view. So originally there is a very clear notion of time, but now it depends on who is looking. Yep.
You've got two entangled particles where the fate of one is determined by the fate of the other, and you determine the fate of one of the particles. Is it correct that no time has elapsed in the determination of the fate of the particle that has not yet been measured? And then since time didn't have, or light didn't have time to reach the second particle, the fate was unknown, it could not have determined the fate of the second particle?
Yeah, okay. I think what he's talking about is a paradox that comes from quantum mechanics, where you can produce a pair of particles in a certain quantum state, and the particles separate with time, and you do a certain measurement here. It tells you something about what's happening at the other end. That in itself is not a big paradox. For example, suppose there are two bank robbers. Okay, they robbed $1 million. This guy took something in his pocket, that guy took something in his pocket. They're running in opposite directions. You catch one guy, he's got $400,000. You know the other guy has $400,000. So you know something about the other person, but you're not influenced the other person in any way. So that's a classical example where knowing something about this will tell you something about that. What is really interesting in the quantum theory is that the money that they take could be in dollars, or could be in Swiss francs, or could be in any currency. And if I measure so many Swiss francs, he will have the remaining money in Swiss francs. That's the surprising thing. Okay? There are many ways in which you can carry the money, and depending on what this person does, you can say something about the other person. But that's not you can show that you cannot use that to convey any information. And the problem really comes from thinking of these two particles as two distinct entities. You're supposed to think in quantum theory of the two particles as a single entity. There's nothing paradoxical about knowing something about an entity and finding something else about the same entity. But look, the laws of quantum mechanics are bizarre in the sense that if you try to explain them in any classical way, you will be forced to conclude that there is a spooky action at a distance. That's because quantum mechanics is weird, and that's just the way it is. So there are a lot of things which are extremely weird even to the practitioners. We don't like it, but we love it. Okay. All right. Well, I would say even half the velocity of light. With very sensitive instruments, you can find the effect due to very much smaller velocities. But if you and I wanted to see it with naked eyes, I don't know, you can ask my colleagues, but it should be comparable to the speed of light. So the velocity of light divided by, your velocity divided by velocity of light should be a number that's not much smaller than 1. If it's like half or 0.5 or 0.8, then you will see dramatic effects. The particles in accelerators are going at a speed so close to the velocity of light that their lifetimes are inflated by enormous factors.
Other question? The person moving through space with acceleration doesn't age.
Yes.
To himself, does not age, but for the amount of time it takes you to jump.
Well, if you really look at that person will know that he or she is accelerating if he is going in a circle. You will be aware of that. Or if the person went in a straight line for a long time, then turned around and jumped on a train going the opposite way and came back, during the straight journey, the person will be aware of nothing. But during the time when you jump from one train to the opposite moving train, all kinds of terrible things will happen to you. You'll be aware of that. That's correct. You'll be aware of your acceleration. You will not think you're aging any differently, but you will agree that there are periods when you're aware of your motion. Yes?
You wouldn't be aware.
Pardon me?
You wouldn't be aware of the passage of time if you were.
Well, actually, it's a pretty funny thing. Here is something I cannot really explain with my hands or with this board, but everything happens when you jump from one train to the other one. Lots of action is cramped because that's where the difference is going to be explained. As long as you're moving at a steady speed, you can think the person on the ground is aging slower than you. On the return trip, you can pretend the person is aging slower than you. in the end, you still have to concede that you're the one who's aging slow, and that all happens during the short period in which you jump from one train to the other. The notion of now in one train and the notion of now in another train are very different. And your whole life literally will pass before you when you make that jump. Yes?
Okay, so in the study of relativity, do you ever get to a point where you find yourself unable to like intuitively explain things to yourself that you can only rely on the mathematics?
Perhaps not in relativity. I think relativity is very simple in terms of mathematics. It doesn't even require calculus. It just requires algebra. And you follow the mathematics, and you follow the chain of logic that I explained to you. So we can see the logic clearly. But phenomena are hard to understand. I agree with you. They're not intuitive because we are bred on Newtonian mechanics. But it's not as mysterious as quantum mechanics, where really strange things happen. I think most people would concede relativity is qualitatively different from our life. Quantitatively different, but qualitatively not so much. Because still, you can follow things and they move and they do various things. In quantum mechanics, you cannot even say where anything is and what it's doing. That's another bizarre world. There, I think your only hope is to describe it mathematically.
One more question. When a photon is emitted, one photon is emitted, is it going in one direction or is it going everywhere? And then measured, looks like it went one.
Okay, well, first of all, if you turn on a light bulb, stuff is going everywhere. Many photons. Well, individual photons can be made to go in a particular direction. You can emit photons in a particular direction if you want. That's correct. A given photon has a momentum that points in some direction. That's the direction in which it's moving.
Other questions?
Yeah?
Is thought faster than light?
Is thought faster than light? Well, I'm a slow thinker, so I don't know how to answer that. Right. Maybe we should wrap it up now and let everybody go. Okay, thank you.